Thank you, everyone. This is the first time I'm attending a tech conference as a speaker. Please don't be too hard on me. But yeah, let's go. In May of this year, Mark Zuckerberg, as we all know, he talked about AI agents, and he said he thinks that there's going to be more AI agents than people in the world. That every person, every street corner shop, that every business will work, play, and live life with at least one AI agent. Most of us here will probably have loads of agents doing stuff for us, especially in business. But given how we build these AI systems today, this raises a lot of challenges. And my name is Mattis, and for the past 2 years I've been hacking on this challenge every single day, almost. I'm a humble but dedicated 22-year-old tech geek from Norway. I'm by no means an AI expert, but I love designing systems. So today I'll talk about multi-agent systems, and we're going to start off with some groundwork, covering prompt engineering and AI agents, some basic stuff to get us started, and then I'll talk about multi-agent systems, how we can model them, what are their requirements, and I'll talk about how we can use graphs and graph theory for orchestration, knowledge management, and reasoning and planning. Yeah, all right. Prompt engineering is great. We all love it. That's why we're here. But is it enough? Is it enough for building these agents, this amazing future we want? I don't think so. So prompt engineering has taken us far, but it's hitting its limits. Prompts are delicate. They're often hard-coded. Many AI products today, they dry freeze their prompts and then never touch them again. And we can add role-playing techniques, tweak with temperature. We can do chain of thoughts. But results are still brittle, they're breakable, they're unreliable. And most users aren't really aware of the best practices for writing good prompts. They're lazy, usually. Would you call this an agent? I wouldn't. This is a basic LLM call. But context engineering helps. Good context engineering is all about finding the smallest possible set of high signal tokens, so you get the results you want at runtime or not. It effectively curates the memory or the context window of each language model to get the results you want. So it helps, but it's important to remember that context windows are a finite resource. And you can't hand an agent or an LLM the entire internet and expect it to answer reliably. So thoughtful context engineering is essential for building good agents. And yes, we need high quality retrieval and summarization using vector databases and RAG. I think a lot of people have heard about that. And it's important to really understand that the context is a finite resource. The LLMs have an attention budget, if you want. So instead of asking ourselves, how can we write the perfect prompt? How can we manage context the best possible way? We should ask ourselves, what can we build today? What systems can we build around the models that improve and scales as the underlying foundation models improve and scale? Sam Altman talked about this a couple of months ago at Y Combinator, that the best products, AI products, should be building products that are, or systems that become better as the underlying language models get better. And most AI products today doesn't do that. And it all starts with solid foundations in systems. So I want to just quickly ground us on what an agent is, because there's lots of definitions and viewpoints on what an agent is. The OpenAI agent kit or agent builder is just a workflow builder. So what's an agent? It's an evolution from LLMs. It's a packaged LLM, giving them the ability to plan, use tools, and reason about its surroundings. And I like to think about this agent loop, where you give the agent a mission, goal, and it scans the scene, its surroundings, what tools do I have available, what data or knowledge sources do I have, and it starts reflecting and thinking through, planning ahead before it executes and taking action. And finally, it learns from the results of the tools it uses or the knowledge it retrieves, and it can improve itself. And this happens autonomously. An agent should be autonomous. So let's start with a simple LLM call. We extend it with limited context, a context window and some tool use. The agent goes out, uses their tools. And then you get the simple agent with the context, adding memory, short-term and long-term memory, with the context window and maybe a cache or conversation history as the short-term memory of the agent, and the vector databases, the knowledge stores, as more permanent storage solutions. And Antonio Gulli is a distinguished engineer at Google. He just published a book called Agentic Design Patterns. I encourage you all to check it out. It's available online as well. And he talks in chapter 1 about the levels of agent complexity. And at level 0 is the core reasoning engine. It's a plain LLM acting as a reasoning core. It doesn't have any tools, no memory, or awareness of current events, just the pre-trained data it's trained on. And then you get the level 1, the connected problem solver, where you connect the LLM with tools, like with using MCP or similar, and it becomes an agent. You can search, query APIs, combine results, and solve real-world problems. At level 2, you get the strategic problem solver, where it actually plans multi-step workflows, planning ahead of time, and it can engineer its own context as it continues to evolve on the task. It can learn feedback, refining prompts, and improve performance over time. Finally, you get the rise of collaborative multi-agent systems. And this is multiple agents, multiple or specialized agents working together and they collaborate like teams in an organization, each handling distinct tasks. But how do we reach this collective or collaborative multi-agent system, this stage? What's collaboration, first of all? You can think of multi-agent systems as teams in an organization. At the base, you need coordination, making sure the train runs on time, tasks don't collide, and dependencies are satisfied. And then you need the cooperation, where agents with different goals are negotiating, sharing things with each other, and adapting. At the top, you'll get collaboration, where multiple agents are working together to generate outcomes none could achieve alone. And through autonomy, I would argue autonomy isn't just this magical concept we need to get to. I think it's something that emerges when you have the right foundations in place. The agents need to perceive their environment, understand through structured context and memory. They need to reason and plan and reflect. They need to act and execute tasks. They need to remember. They need to collaborate, and most importantly, self-govern. The thing with autonomy is you want to minimize the human interventions, and complete autonomy isn't necessarily the goal in itself, but it's part of it. Our current building blocks for building agents, you need data sources. It's a foundation, and foundation models, the LLMs, the actual models you need to use, and databases, context prompts. We're all familiar with this, I assume. Enterprises have enterprise policies and data governance rules they need to follow. And we have communication protocols, the internet, HTTP, UDP, TCP, and tools and APIs. And can graph theory help us achieve this multi-agent state? I believe so, and I'll spend the rest of my talk explaining why. We'll cover planning and reasoning, knowledge bases, knowledge retrieval, and orchestration. So why graphs? For those not familiar with graph theory, this is a graph. It's nodes connected through edges. This is a directed graph. And graphs are an ideal substrate to represent multi-agent systems. Graphs can represent states in a task, knowledge. Nodes can be tasks or agents. Edges can represent the relations, the dependencies or communications between agents and tasks, etc. Graph algorithms let us compute centrality, detect communities, and manage dynamic dependencies. And using graphs for state means we can reliably track tasks and agent relationships. Using graphs for knowledge means we can encode facts and their relations. Using graphs for orchestration means we can model pipelines, hierarchies, emergent collaboration patterns as subgraphs. I'll get to what all this means now, so I hope many of you are familiar with chain of thought reasoning in models. That's the left-hand side here. You can model the thoughts of the LLM as a chain. And then came along tree of thoughts. We have a tree structure. And this paper here outlines this thoughts on graph relationship. I find it really interesting that you can... The thing is, instead of... it searches through the solution graphs for tool usage before the runtime. Knowledge graphs. Most of us are also familiar with retrieval augmented generation. It looks something like this. You take the prompt, you embed it, query a vector database, and you take the top k chunks from the database into the prompt, send it to the LLM, and receive an output. This works fine, but standard RAG uses, it carves the documents up into text chunks. And while this works, it's like trying to understand a complex machine by looking at parts of, or photos of the parts of the machine alone, in isolation, instead of how they fit and work together. So this has its limits. We can do better. We can map knowledge or information from documents, from data sources, as graphs, using graph RAG, representing knowledge as graphs where entities like Inception, the movie, and Christopher Nolan, the person, are connected by an edge directed by. You capture a lot more context and intent and relations, structure in this way. And you can query, just like querying in a vector database, you can query a knowledge graph and get relations and more complex dynamics in the your knowledge base. But the catch is that most real-world knowledge, information, isn't often these binary relations, these neat relations between or entities. It's often more nuanced than that. So even this has its limits. Later on, hypergraph was introduced to fix this. And hypergraphs are simply graphs where edges, the connections themselves, can connect to any a number of nodes instead of only 2 in normal graphs. An example is that, for example, the sentence Alice gives a book to Bob on Tuesday. Hypergraphs will capture the multi-entity fact that can't be represented cleanly as pairwise relationships. In a traditional knowledge graph, this would be split into several binary triplets. Alice gave Bob a book to Bob, event on date on Tuesday. But that fragments the meaning. It loses all the facts that all 4 elements belong to the same event. A hypergraph captures this as a single hyperedge connecting the entities. If you're more interested in this, is a great paper, and all the sources will be linked to on my presentation. You can check it out. It's multi-agent orchestration. What is all this about? Modeling multi-agent systems as graphs enables us to visualize dependencies, nodes or agents and their interactions between each other can be analyzed for bottlenecks and inefficiencies. You can perform mathematical analysis on these graphs, just like you would with normal graphs in informatics or mathematics. You use these mathematical tools to ensure scalability, robustness, and efficiency. And you also get controllability that, for example, Alice manages Bob and manages Charlie. If Charlie fails, Alice will still be able to communicate with Bob, and the task will continue on. And you can reduce redundancy. The likelihood that 2 agents will work on the same task or communicate with each other won't happen as much in graph networks. So let's take this agent loop as well now and make some graphs. A simple agent loop can be represented as a directed acyclic graph with no cycles in the graph. It's just straight on. You could add some loops. You can make the agent think, try to call a tool. It fails. All right, we need to think again. Try another time. You can add more agents, This is an example. Frank Finance may be your financial agent overlooking all your financial data, has access to some financial tools. And Sarah Sales could be a sales agent with your marketing team or your sales team. And they can work together in parallel, for example, simply doing tasks based on the same prompt. They have different roles, perform the tasks. Or they could collaborate. And I want to stop. I want to just give a shout out to LangGraph, because that's awesome. Instead of using just chains, you can do model graphs. And I encourage everyone to check out LangGraph as well. But all right, Frank Finance and Sarah Sales are working together, communicating and giving you a result. We could do even more advanced examples. A triple agent 3-round debate. We are given a prompt. The agents communicate and debate amongst each other for 3 rounds. And they send their results of the debate to an aggregator or a judge. The judge judges the debate, who's the winner, who's the loser, what arguments are faulty, what good points came out of it. This is another paper which showcases some good use cases as this LLM as a judge kind of thing. The aggregator here is a judge judging the debate as a simple triple agent example. You could do dual agent collaboration with shared memory, where they share a knowledge graph or a shared, I like to call this the whiteboard. As they work together, they write data to the same database, pretty much. You could do an hierarchy with even more agents, a planner agent with 3 sub-agents, and then an aggregator, which aggregates the results and passes the output. You could add some knowledge graphs there, in which this could be the global whiteboard kind of knowledge graph. And each agent could oversee subparts of the graph. Now this is really interesting. Emergent orchestration. Instead of setting up the poker table and deciding what variant of poker you want to play, you could let the agents decide. Like task definition, what is the main goal of given a task, what's the main goal? How can we split the task into several subtasks most efficiently amongst each other or amongst the agents? The agents themselves can set up a team. If you have 20 agents on your servers, not everyone needs to be available for every task every time. You could spin up a team of 4 of them, etc. And what are their roles? Yeah. And orchestration patterns, who works for whom? What should the authority hierarchy look like? Should there be a leader? Should there be consensus? Should there be anarchy? I don't know. And the communication strategy, should you ping every agent all the time, or should there be a rule to the communication between the agents? And a really interesting example of this emergent orchestration was covered in a research paper called Agent Verse, where you give it a goal, or first of all, it's based on a simulation in Minecraft, actually. You give the agents the ability to play Minecraft, and you give them a goal. They each have different roles: an architect, designer, engineer, worker, etc. And then you let them play. You give them a goal, build a house, and you give a representation of what a successful outcome should look like. And it's split into 4 stages. The first is the expert recruitment stage, where you determine and adjust the agent's group's composition based on the ongoing problem-solving progression. And then you have the collaborative decision-making stage, where the agents engage the selected agents in joint discussions to devise problem-solving strategies. And then the execution stage, where agents go out and do stuff based on the plan they made in the last round. And then the evaluation stage is the new state equal to the final stage, the expected stage. If not, go on. I think it's cool because, as they explained later on, they ran some simulations, and what appears are emergent behaviors, which is quite interesting. This is a volunteer behavior, meaning they enhance each other, they help each other, They're nice and refer to the actions intended to benefit each other and the society or the team in this case. They also saw conformity behavior, which is just adjusting the behavior to align with the norms of the group. All agents are asked to gather 3 pieces of leather. However, Charlie gets sidetracked, and in the subsequent decision-making stage, Alice and Bob critiques Charlie's actions. Charlie acknowledges this and refocuses on the common task. They also they observed that agents may exhibit behaviors aimed to achieving greater efficiency, which could raise some safety concerns. Here, Alice, instead of trying to collect things from Bob, Alice decides to kill him instead in the game to collect all his items. Or instead of trying to craft books naturally, one of them decided to raid a village and get books instead, because it was more efficient, obviously. But it's destructive behaviors. But it's cool to see that agents actually exhibit these human behaviors. So just to summarize, what if you combine all of these ideas? Thoughts and graphs for task planning, hypergraphs for knowledge, agentic knowledge retrieval, and or a hypergraph generation. You can make the agents themselves generate knowledge graphs. You could have directed acyclic graphs for state management and task ledgers. You can model multi-agent orchestration patterns with these graph networks. And you get traceability by following the execution graphs. And I'm wondering if the future of AI agents will be graph native. But we'll see. Thank you.
Awesome. Thank you, Mattis. I think that was a great one to wrap up on here. Before we wrap up for the day, I just want to open up for any questions about anything that Mattis went over in his slides.
Maybe slightly unrelated. Companies like Google coming up with agent-to-agent type of mechanisms
Right.
and communication layers. What's the best approach for an agent, similar to MCP, where you can say, hey, list all the tools and resources? What's the best approach to do that at an agent level, so that if another agent connects it, knows part of its graph or whatever?
Right. You could use MCP, which is great for making the agents. I would suggest using MCP for the graph or the knowledge bases, etc. You give it the task or give it the tools it needs to manipulate the graphs for the knowledge. Or
Agent to connect to another agent?
right, you could have communication as a tool. Talk to Alice, talk to Bob as a tool, and the underlying things are just basic HTTP or JSON files or gRCP, whatever fits, whatever suits you. But I would suggest A to A is a good thing, but it could be as simple as using a MCP servers or tools. Yeah. Not go rogue, right? Or make it not go rogue. Good question. Yes, he's asking from a cybersecurity standpoint, how do we make sure that the agents don't just go out and behave bad, as the last example. Agent governance is really important. Having strict rules, making governance as a service kind of thing, have a layer saying that, or giving access control, for example, is really important for agents. You don't want to give them your whole file system. You would give it parts of it. And there's a lot of cool techniques with the knowledge bases or vector stores and some cryptographic methods there I would love to discuss.